Welcome back. We are in week 6 of inverse methods in heat transfer. In the last video, we saw the idea of expectation, which is just like a mean or an average, which we can extract out of a probability density function. Now, we are going to look at a second quantity, which is similar to the expectation. The expectation sort of gives you the average mean of a quantity, whereas variance tells you a fluctuation over the mean. Obviously, no quantity is going to look fully like the mean. So if it looks fully like the mean, all it will look like is this. Usually, however, random variables are defined by their fluctuation. Okay, we are not going to get fully mean. So at the very least, in order to understand a variable, random variable, you need these first two things. You need an expectation and you need a variance. As it turns out, you might require a whole lot more, but at least we need these couple of things. Okay. So random variables, as we saw earlier, they result in different outcomes. Their variation is captured completely. I'll emphasize this again only by their distribution. So this is the most important thing which has captured completely, as I wrote in the last video. It's captured completely. So a full sort of simple example, not an example, a simple reduction of this random variable is given by the expectation. Okay, so instead of asking how well did each boy do in the exam, you can ask, oh, boy scored 60% in 10th standard board examinations, whereas girls scored on an average 70%. So that's the expectation. Okay, but you also should look at the variance. So for example, if there is a large amount of variance, that says something. If there is a small amount of variance, if every boy scored only around 60, 61, 50, 59, 61, that says something. But whereas a lot of boys scored 0 and a lot of boys scored 100, and in the middle it was completely different, that also tells you something else. So expectation by itself is insufficient for us to find out what a distribution looks like, which is why we look at the first kind of quantity, which is the variance. So the variance gives us variation from the expected value. So notice this, variance is always with respect to the expectation. So variation from the mean. Okay. So for example, variance, as I told you, you can talk about mutual fund. What is the average expected return? Let's say somebody says 10%. But what is the risk? The risk is how much will this fluctuate? Just like we have electricity fluctuations, it is not just important to know what the actual or the average voltage is, but you want to know what the fluctuations. Similarly, temperature, average temperature in my cell phone is, let's say, 20 degrees centigrade. That is less important than the variance. If the variance is like 50 degrees up, then we are in trouble because it can hit 70 at any time and it basically can blow up. Okay, similarly, variance in rainfall tells you how heavy a rainfall can get, even if average is slightly low. Okay, so variance is an important quantity. So the first thing we will look at is what is known as univariate variance, which is a simple single variable x. Okay, so what it measures is how much the value of f of x varies for various samples when x is drawn from P. Very similar to what we did with expectation. I have written the general formula for f of x. You can simply think of variance of x also. Okay, so that is easy. But the same thing as last time, I might write x drawn from P. Simply write x when P is obvious. Drop that x also when x is obvious, or you can simply write variance of f. Now, mathematically, variance of f of x is given by this kind of complicated looking thing, which is expectation of f of x minus expectation of f of x the whole square, which is why I'm going to use the notation like before. The expectation of f, I'm going to call f bar, which means average of f. So then it is easier to see. You find out what the function is, find out what its deviation from its average is, square that, and then average it once more, and that gives us the variance. So variance is basically like mean squared of f of x. Now, a special case is what is variance of x? Variance of x is simply expectation of x minus expectation of x, the whole square. Another way of writing it, which we did earlier, is remember when we did coefficient of determination, expectation of x minus x bar, the whole square. Again, mean squared deviation, mean squared of deviation of f of x from its mean. So mean square error, where error is defined as how much x varies from its average, is what this is. Another way of writing it is x minus x bar square, the whole bar. But this is a little bit more confusing. So we can use a mixture of these two notations. So expectation, once again, of x minus x bar square is basically variance of x. How much does x vary over its mean? That's what it means. The standard deviation is, of course, root mean squared, which is given as square root of the variance, as you can see here. Okay, that's the standard deviation. It's given by sigma. Now let's come to covariance. This covariance is usually for a pair of variables, x and y. Okay, so two variable case. Okay. We first look at what variance is. The variance is expectation of, as I just wrote, x minus x bar, the whole square. So you can write it as a product of two things, x minus x bar multiplied by x minus x bar. Similarly, we define the covariance of two variables, x and y. Now, what does this mean? We will come to this. This is a very interesting meaning. We'll come to this meaning shortly. But what it is this expectation of x minus x bar and expectation multiplied by y minus y bar. What this says is, how much does the fluctuation in x move along with the fluctuation in y? Do these two align with each other, or are these two completely misaligned? Okay. So another way of writing it is, of course, the more formal way of writing is x minus e of x, y minus e of y. But like I said, it's preferable to use this when you write it, because you might get confused when you write it on paper. Similarly, covariance of, here I wrote covariance of x comma y. More generally, if you look at covariance of f of x, g of y, which is expectation of f of x minus expectation f of x, g of y minus gy bar. Okay. Now, a very important related quantity is what is known as correlation, which you can think of as normalized covariance. Okay. So covariance by itself might be high or low. We can't make much out of it. But if we divide by this quantity, square root of v of x multiplied by v of y. Okay, why is that? So if you look at this, look at the size of this. This is expectation of delta x multiplied by delta y. Let's call it that. So instead of expectation of delta x comma delta y, we want to find out a normalized way. I divide this by expectation of delta x comma delta x, or expectation of delta y comma delta y. But of course, there are two of these, so I put a square root just to get the same size here. So this becomes expectation of a square root of variance of x multiplied by variance of y. Okay. Now, what this correlation measures is, this is really important. So please notice this. It measures how linearly correlated. The word linearly is very important. how linearly correlated these two random variables are. Okay. So if you notice what covariance of x comma x is, so covariance of x comma x is of course expectation of x minus x bar multiplied by x minus x bar, which is simply variance of x. Okay, so that's what is written here. Covariance of x comma x is variance of x. But what is correlation of x comma x? Correlation of x comma x is covariance of x comma x divided by square root of variance of x multiplied by variance of x, which is covariance of x comma x is variance of x divided by, of course, this is also variance of x, which is 1. An interesting exercise that you can do is, what is correlation of x comma some constant multiplied by x? Please find this out and see what it is. That's an interesting exercise for you to do. Okay, so coming back to this, notice two things. Covariance of x comma x is variance of x, and correlation of x with itself is 1. So we are now going to use these relations to interpret what covariance and correlation actually mean. So here I have drawn a few plots. Let's concentrate on each one of these plots one by one. These are some random variables x and y. Okay, so x is some random variable, y is some other random variable. And we collected data. Notice a lot of this joint data. Let's say there are about 100 points here. Okay, randomly generated points for x and y based on some relation. Now, overall, you can see, just like our slab temperature, there is an increasing trend. That as x increases, overall, you can say y increases, but that doesn't always happen. It is possible for x to increase and y to decrease. So, for example, this x is lower, this x is higher, but this y is higher and this y is lower. So, y does decrease occasionally, but overall, it increases. So how do we capture this idea that there seems to be some relationship between x and y? They are not just totally randomly related. So that's what covariance and correlation do. Covariance is positive. It's a positive value. But is this value high? Is this low? We don't know without normalizing it. So correlation is normalized. We know that if x was plotted with x, this would give us exactly 1. This is 0.97, which is pretty close to 1, which is these are very nicely linearly correlated. You can see that here. And this positive value, in fact, indicates that whenever x increases, in general, on an average, y will increase. It's a powerful quantity. Look at this here. Exactly the opposite relationship. When x increases, y decreases, though not always. Again, like I said, sometimes it can happen that x increases, but y increases also. But overall, the trend is a decreasing trend. Okay. In such a case, we look at the covariance. Covariance is negative. Again, is this big or small? We don't know, but we can look at the correlation. Normalized correlation is minus 0.98, which means that it is very close to plotting something like x versus minus x. So this is perfectly, almost perfectly negatively correlated, which means it will decrease, but the two variables are correlated. Now compare this. Covariance is 8.53. We cannot interpret covariance as except that it is positive, but it's a meaningless positive. Correlation is 0.14. What correlation is 0.14 says is that there is practically zero linear correlation between x and y. You can see these are just randomly distributed. You cannot see any kind of trend here. Okay. So what we can say is positive covariance means x increases, y is expected to increase. Negative means when x increases, y is expected to decrease. Correlation close to 1 means strongly positively correlated. Correlation close to minus 1, like the minus 0.98 case, means strongly negatively correlated. And correlation 0 to close to 0, like here, means no linear correlation. What does linear correlation mean? Let me show that in the next couple of slides. Let us just do a quick simplification here, which we will use in future also. So there is this nice relationship which says that covariance of xy is equal to expectation of xy minus expectation of x multiplied by expectation of y. So we had seen this earlier also when we were looking at the linear regression, that expectation of x comma y is not the same of expectation as x multiplied by expectation of y. In fact, their difference is exactly the covariance. So that is what we are going to look at right now. We are going to use a simple fact here that the average of the average is the same as the average, because the average is no longer a random variable. So expectation of x is the same as expectation of x. So we will use that. So let's start here. So the covariance of xy is x minus x bar multiplied by y minus y bar, the whole average. Okay, so I'm going to use this expression. So let's open this up. I'll call this expectation for now. So this is expectation of xy minus x bar y minus xy bar plus x bar y bar. Okay. So we have our linearity of expectations. So we can add this up. This is expectation of xy minus expectation of x bar y minus expectation of xy bar plus expectation of x bar y bar. Okay. So this is xy average minus x bar is a constant. So x bar times y bar minus again x bar times y bar plus x bar y bar, the whole bar. So this is, of course, this term, I'll just leave it as expectation of xy. This term is, these two terms are the same, and they are minus expectation of x, expectation of y, and of course, there are two of these, plus x bar is a constant, y bar is a constant. It can be taken out of the expectation. So really, this is just average of 1. So this is once again expectation of x multiplied by expectation of y. So this is expectation of xy minus expectation of x. So these two add up multiplied by expectation of y is covariance of x comma y. Okay, so that's the proof. There is a special case here. When x equal to y, this tells us that covariance of x comma x is expectation of x square minus expectation of x, the whole square. But covariance of x comma x, as we saw earlier, is simply variance of x. So we have this relationship that variance of x is the difference between the expectation of the square minus the expectation whole square. So this is a very, very useful relationship. Okay, so we often use this to find out the standard deviation and many other things. You would have seen this in school also. X square bar minus x bar square. Okay? Another way of writing it. X square bar minus x bar square. You might remember this also sitting in our linear regression formulae, which are there. They are there for a reason. It's because it's a physically very important quantity. Now, I talked about how covariance means correlation equal to 0 simply means that these are not linearly correlated, okay, or they are not linearly dependent. Okay, so that's a very important statement that was made, that statement being linearly. So let's look at the implications of that statement. So let me show this with an example. So there are two statements. The statements are this: if x and y are independent, if you take two independent variables and write or find out their covariance will always be 0 or close to. If they are truly independent, then fully 0. If not, they'll be close to 0. So here is an example. In this case, covariance has to be approximately 0. Okay, especially correlation has to be close to 0. But the opposite is not true. That is, if covariance is 0, it does not mean that the variables are independent. It could mean they are independent, but you cannot always infer that they will be independent. Okay, so that's what I have written here. Covariance xy is 0 does not mean that x and y are independent. So let's look at one such case. Here, x and y are random variables. Okay, so x is a random variable. You can see it's randomly distributed. Y I defined as x square. So clearly x and y are not independent. Okay, you can see y depends on x. There is a nice clear trend. Then should covariance be 0 or non-zero? Now, if we think that correlation simply means, or more than covariance, let's talk about correlation. Should correlation be 0 or not? Looks like they are dependent on each other. Correlation should not be 0. And in fact, I should get a nice value. But unfortunately, it turns out that correlation actually will be 0. Okay, actually will be close to 0 here. If you use the formula that we had, even though x and y are not independent. So covariance equal to 0 does not mean independent. Why is that? So let's look at this. Covariance of x comma y is expectation of xy minus expectation of x multiplied by expectation of y. This is expectation of x cube minus expectation of x multiplied by expectation of x square. Now look at this variable x. This variable x goes from -1 to 1. Okay, it's an odd variable. So equally likely it is expected to take positive values and negative values. So expectation of x cube will be 0. Expectation of x square will not be 0, but expectation of x is 0, which means covariance of xy and correlation of xy, if you calculate it, will turn out to be 0. So 0 covariance only means that there is no linear relationship. That is, y is not a linear function of x. So y will not look like some alpha x. Okay, but it could look like, as in this case, it could look like x square. Okay, so this is a very, very important counter example. So if two variables give you correlation of 0, all you know is that they are not linearly dependent on each other. Okay, but you cannot say anything more than that. Nonetheless, correlation is an important quantity in order to figure out linear dependence of one variable on the other. So we do use that. Okay, so in summary, 0 covariance, independence means 0 covariance, but 0 covariance does not mean independence. Okay, we now come to the next important idea. This is a very, very central idea when we go to the multivariable case, a multivariate case, which is called the covariance matrix. We have just been looking at univariate covariance. Now we will look at multivariate covariance. So in many cases, we actually have multiple variables, just like in the case of a slab. I can think of x as all the temperatures put together, as I said earlier. So x could be the random vector T1 through T6. And now we can start looking at pairwise covariances. That is the temperature here independent of or linearly independent of T2? Is T1 independent of T3, etc.? So we can now think of what is called a covariance matrix. So you can make a full matrix. Each of them is the pairwise covariance of any two of these variables. So basically, simple idea, you write covariance of x comma x, ij, which is covariance of xi, xj. So first variable with first variable with second variable, first variable with nth variable. Of course, it is a symmetric matrix because covariance of x comma y is the same as covariance of y comma x. So it's a symmetric matrix. The second thing to note is all the diagonal elements. Okay, so if we look at just the diagonal elements here, these are simply the variances. Why? Because covariance of, as we saw, xi is simply variance of xi. So what this measures is if this thing is diagonal, then we can say that at least all the xi are linearly independent. So the closer this matrix looks to the diagonal, and we'll often make this assumption while making inverse problems, is that we are assuming that linearly the measurements are independent. I'm going to show a more specific case when we come to the next week. But notice that the diagonal elements are the variances and the off-diagonal elements are the pairwise covariances, which we had defined earlier. Now we have looked at a series of ideas: expectation, variance, covariance, etc. So just to sort of round this off, I'll show you a couple of very, very simple examples. Something related is also sitting in your exercise for this week. And after that, we'll move to the next topic, which is Gaussian distributions, which is in the next video. But for now, let's just take a couple of simple examples. So let's take this example. There's a density function of x, which is the probability density function of x. It's given by this simple formula. F of x is a plus bx square if 0 is less than x is less than equal to 1, or it is 0. So the probability distribution function would look something of this sort. Okay, so this 0 here, 0 here. Remember, PDF always has to be positive. Okay. So you're asked to find out what A and B are, given that expectation of x is 3 by 5. Okay, so this is also given to you, and you're asked to find out. So you have two things to find out, and you are given one piece of information. So let's go ahead and do that and see how to think about this. Clear? Now you might think that this is an absurd problem, like no such problem would occur in reality, but as it turns out, this is a very important problem in approximation of PDFs. As I told you, we don't usually have actual probability distribution functions, but we will have some of their properties, like we will have their expectation, we will have their variance. And it's an important exercise to model these probability density functions as some simple PDFs, and then go ahead and recalculate what these functions are on the basis of this. So let's come back here. So let's say expectation of x is 3 by 5. What else do I know? I know that the probability density function has to integrate to 1. Why? Because the net probability always has to be 1. So this is one equation. The next equation is from here, which tells us minus infinity to infinity x times f of x dx, which is the probability density function, is equal to 3 by 5. Now we will use these two pieces of information to figure out these two variables, a and b. So let's take the first. So the first one says a plus bx square dx. The integral is minus infinity to infinity, but it is non-zero only between 0 and 1. With 0 and 1 is 1, which when you integrate, this gives us a times x 0 to 1 plus b times x cubed by 3, 0 to 1 is 1. So this gives us a plus b by 3 is equal to 1. Similarly, the second equation says x times a plus bx square dx 0 to 1 is 1. So this gives us a times x square by 2, 0 to 1, plus b times x power 4 by 4, 0 to 1 is 3 by 5, not 1 here, sorry. It's the expectation. So this tells us a by 2 plus b by 4 equal to 3 by 5. Now we can easily solve these two equations together in order to find out a and b. So we can simply multiply this equation by half and subtract it from this equation. So that gives us b by 4 minus b by 6 equal to 3 by 5 minus 1 over 2. So this gives us b by 12 equal to 6 minus 5, 1 by 10 So B is 1.2 and this gives us is 0.6. So A equal to 0.6, B equal to 1.2, and this is a simple way of solving this. Of course, we could have extended this problem to a more general problem and given, let's say, a C. So I could given a CX cube, and then I would need some extra piece of information. I might ask you to give the variance of X also. So as I give more and more information, you can find out more and more parameters for this probability density function. So that's a powerful way of using our these are called moments. So for example, you can see this is integral of f of x. This is integral of x f of x. The third one will have terms which involve integral of x square f of x. Of course, it's x minus x bar, but generally it will involve terms involving x square f of x, and that's what makes this whole thing very powerful. Okay, so very flexible in finding out probability density functions. Let me give one more problem. This is sort of related to the previous problems that I gave or examples that I did. So let's say you are taking part in a betting game and you have a biased coin, okay, which is tossed n times. So let's say the biased coin has probability of heads equal to P. So P could be something, let's say 0.6, 0.7. It's not necessarily equal to 0.5. Okay. So once again, it's sort of a flip of what I told earlier, or maybe the same, that you're given ₹1 for each toss of heads and nothing if you obtain tails. So what is your expected value of gain after n tosses? So that is the question. So remember, we now have to define carefully what our random variable is, what our expected value of our random variable is, etc., etc. So let's do that and then solve this problem. So let's define our random variables carefully. So let's say we are making n tosses and each toss corresponds to a random variable xi, or the gain that you gain. So gain a toss I is xi. So you get 0 if you toss a heads, and you get you get 1 if you toss a head and 0 if you toss a tail. Okay. Remember that probability of a head is P as we defined here, and X, your gain after n tosses, is x1, what you will get after the first toss, what you will get up until xn. Okay. Gain that you get only at toss I is this, and x is this. Okay. So now what is expectation of xi? That is at the ith toss. Remember, you get 1 if you get heads. So the probability of this is P. Okay. When you get 0 if tails, the probability of this is 1 minus P. So the expectation at the ith toss is sigma of xi, P of xi. So this is basically 1 with probability P and 0 with probability 1 minus P. So the expected gain at the xith toss is P. So therefore, the expectation after x at x is sigma. Actually, I should do it in 2 steps. Expectation of x1 plus x2 up until xn, which, if you remember, is the same as expectation of x1 plus expectation of x2 plus expectation of xn. So which basically is n times p. So our expected value of our gain after n tosses is simply n times whatever is the probability of getting heads. So this is very obvious. If you say that the probability of getting heads is 0.6 and I did 100 tosses, what do you expect to gain after 100 tosses? You will say, of course, 60 rupees. But we have a more important or interesting question. What is the variance in your gain? So one person tossed 100 and got 60 rupees. Another person, is everybody going to get 60 rupees? No, obviously, different people are going to get different number of heads, and depending on their luck, they might get slightly lower or slightly higher. What is the variance? Can we actually say something about the variance in this gain? So we are going to ask that question, and we will answer it in a slightly roundabout fashion. So to answer that question, we have to go back to when we did sums of random variables. Okay. So I cheated a little bit. I said that expectation is a linear operator, which is true, but it was a linear operator in one variable, and I kind of applied it so far to two different random variables where it also holds true. Okay. It turns out that this is also true. There are subtle differences between these two cases, but I'm not going to get into that. This also happens to be true. So we are going to use these forms rather than this form. Okay. Rather than taking two different functions of the same variable, we are going to take two different random variables altogether. Okay. So x is a different random variable and y is a different random variable, and we are going to take sums of that. It turns out expectation is linear there also. However, variance is a little bit more involved. Okay. So variance is, it turns out, variance of x plus variance of y plus 2 times covariance of x comma y. You have to be careful if x and y are vectors, which is why I wrote it separately. But in case they are just scalars, you can treat this as 2 times covariance of x comma y. So notice that if x and y are dependent linear variables, then this doesn't cancel out automatically. Only if x and y are independent, then you see that variance of x plus y is variance of x plus variance of y. Similarly, variance of alpha times x is alpha times variance of y. So you have to be a little bit careful about how you do these things when variances are involved. So we'll see that shortly in the continuation of this video. Please also think about what happens to variance of x minus y. Okay, so this is a interesting question that you can answer for yourself as an exercise. So remember these expressions: variance of x plus y is equal to variance of x plus variance of y plus 2 times covariance of xy. In general, variance of x plus y is equal to variance of only if x and y are independent. Independent in every way, not just linearly independent, independent in every single way. And variance of alpha x, okay, there's a small error here. There should be alpha square. Okay, so I'll just write that again. Variance of alpha x is alpha square variance of x. Okay, so all these formulae are things that you can prove. I'm not going to prove these, so proof has been skipped. Okay, you can prove this by yourself. It's not hard, but that's beyond the point of the current course. So please try and prove it for yourself. Very similar to the proofs that I have done so far. So we will use this formula here. Okay. So now once again, we are taking part in that betting game where bias coin is tossed n times. What is the variance in your gains after n tosses? So now let's write that. X once again is x1 plus x2 up till xn. Now the question is, are the xi independent? And the answer is yes. If you toss the coin 2 times separately, the outcome of one does not depend on the outcome of the other. Okay. Therefore, you can basically write variance of x as summation of variance of xi. Okay. Now there are various ways of calculating variance of xi. So let's do that. So xi once again is the same thing. It is 1 with probability p and 0 with probability 1 minus p. So we want to, since xi are independent, okay? Because of that, we can write this as a summation of variances. So variance of xi, we can use our formula. Expectation of xi square minus expectation of xi the whole square. Okay. So what does expectation of xi square mean? So xi square is also 1 with probability p and 0 with probability 1 minus p. So expectation of xi square is 1 times p plus 0 times 1 minus p, so which is p. What about expectation of xi the whole square? We had already calculated this in the last part. This was p, so this is p square. So this tells us that variance of xi is p minus p square, which is p into 1 minus p. So variance of x is basically n times variance of xi, which is np 1 minus p. Okay. So you can see that there is a amount of variance in how much gains you'll get. So let's say your biased coin has probability p, which is very, very close to 1. Okay. So very, very close to 1. Your variance will actually, you will actually notice what happens to it. Actually, I will suggest this as an exercise. I was going to say this. So plot what the variance looks like with varying p's and see if you can find out what the meaning is, what values it takes. Why is the variance high in a few cases and why is the variance low in a few cases? That gives you sort of some intuition for how this thing works. So what we did in this video was continued from the previous video. We looked at the variance, we looked at covariance, and we looked at the covariance matrix, and we looked at the sum rule for variance, which said that variance of x plus y is variance of x plus variance of y in case x and y are independent. And we did a couple of problems. So in the next video, I'll move to one of the fundamental distributions. Okay, so we talked about probability distributions in general here, but we look at one of the fundamental distributions, probably the most fundamental distribution in all of science and engineering, which is the Gaussian distribution, also called the normal distribution. So we will see that in the next video. Thank you.